morning, good afternoon or good evening whenever you watch this video. Today I'm sitting here with Kelvin Rens, Associate Professor in our faculty, and you know him from the course on structure analysis and design. And today we want to talk structural design. So Kelvin, thank you so much for joining us.
Thanks.
Let me just drop the hard question here right away. What is the biggest mistake students make in structural design of an aircraft within the DSE?
I think the biggest mistake students often make in structural design is starting and thinking that there is a final solution, forgetting the fact that design is an iterative process. It is a sequence of design decisions. Students are aware of that in aircraft design, in the conceptual design, and they do their first weight estimate based off statistics, get an empty weight fraction. That is your first structural design. And then oftentimes students then jump to, well, let's do a finite element model of a wing box with all the stiffeners. And there's just too much that they don't know before they get to that point. So they get lost thinking this computer tool or these calculations are going to give me the final design. So you have to break up all designs into a series of decisions that you would like to make.
And I guess it normally starts with analyzing the loads, because you first need to know the loads.
You do need to know the loads. So that's, I always say the function of a structure is to carry and transmit loads. So if you don't know what those loads are, you don't know how to design it, or what potential to design within it.
So basically students jump too quickly into structural analysis instead of structural design,
yeah.
You could say.
So like one classic example, when students come and talk to me about their design and they show me a sketch and they're like, we're thinking we need 8 stiffeners on this wing box. And, one of my first questions is, well, what material is it going to be made out of? And they're unsure. And then I kind of question, well, how can you know if 8 stiffeners is going to be sufficient if you don't know the material? And then they start questioning themselves. They're caught up in, we know that we can do these calculations, and I plug some numbers in. And so in design, and in engineering in general, we develop models to give us a wrong answer that is sufficient enough to make a decision. So the starting point in a wing box, I always say, standard thin-walled box, constant thickness, and that's where you should start once you know your loads. Your final wing box will not look like that, but with that you can estimate that thickness, do a comparison of weight of different materials, and maybe get an idea of, if my thickness that comes out from my calculations is 0.2 millimeters, there's definitely going to be some buckling issues. And that might influence your design. Or if it comes out really thick, you might have to think of non-traditional structural configurations. So you always have to be looking at, what is that next decision I want to make, and what sort of model or calculation do I need that is simple to get that answer first.
You spoke about design iterations, structural design iterations.
Yeah.
Can you give me an example of a wrong but still useful design iteration?
Yeah, so for instance, like I was mentioning with that constant thickness box design, you would never make a wing box that has the same thickness on the top and bottom wing skin and the spars. We know that there's going to be differences because of buckling and all sorts of things. But if your initial weight estimate is based upon statistics and an empty weight fraction of similar aircraft, coming up with a model of a constant thickness box that you size for your particular loading is already an order of magnitude more accurate estimation of the weight and some of the aspects that you would need in the design. And you could select material from that. You can assess the criticality of certain failure modes and figure out where your next step would be. So you always have to sort of clearly, we do the same thing in research. You have to clearly state, what is the question that you're trying to answer, the hypothesis, and what do I need to do just to get that?
Okay, and what would be the role of finite element calculations in this phase of the design? Would it make any sense at all, or
Well,
would you be very careful with that?
I tend to say finite element analysis is used for detailed verification of your design. A finite element analysis model is not very conducive to parameterizing thicknesses and numbers of stiffeners.
You're not really a design tool, but it's an analysis tool.
Yeah, you're putting the design in to check the details of perhaps some of your assumptions. Whereas very simplified parametric analytical models where I can put thickness in as a variable or number of stiffeners, and you're iterating the calculations, that needs to be far simpler. Like the amount of time to run a single finite element model is already huge. So you can't run a lot of variations. So you want to examine as many of those variations before you get to the FEM.
Okay, so a bit hesitant there. If you look into structures, we always want to make sure that structure does not fail. Of course, built in a safety margin with respect to that moment of failure. Yeah. But there's multiple modes of failure: shear, buckling, tension, torsion. How do you design for all of them?
Well, the trick is you have to check all failure modes in the end. And certain failure modes will be driving your design. So take the thickness of a wing skin panel. That might be driven by buckling requirements. It might be driven by ultimate strength requirements. You don't necessarily know that beforehand, so you have to set up your models to do calculations for each of those and identify which ones are more critical. And this is where some of those simplified models are useful, because you might be able to see early on that certain things are more critical and will be driving your design. But you can't just sort of set up, equations for the hundreds of different possible failure modes and then push a button on a computer and it will solve everything. Mm-hmm. Unfortunately, it doesn't work out that way because it's a multivariable problem. And in fact, there's probably thousands of designs that could fulfill all the requirements. I say I can design a structure out of concrete that meets all the structural requirements. It'll probably be heavy, but it could meet the requirements. And so you also have to bring some judgment on that.
What type of tools would be suitable for that? Would you think about Python, MATLAB, Excel, or are there online tools available for that?
Yeah, there indeed. You can set stuff up in Excel. I don't usually like that because things are hidden. But indeed, a Python script or MATLAB script or some sort of calculation sheet. I used MathCAD a lot in my past. I know students have access to that, where you spend a little bit of time setting up the calculation and documenting it so that you can rerun it and update it relatively frequently. But even if you do something in Python or any of these scripts, also please at least do it once by hand. I can't emphasize that enough, that it's very easy to make very simple mistakes in typing up scripts in that. And so you should always do it the old-fashioned.
Yeah, just some basic engineering bending theory to see what it really makes sense, a deflection
or do sensitivity studies. See, like if I change this loading, the classic one is if I increase the loading, does the thickness go down and the weight go down? That doesn't really make a lot of sense. So there's little ways to do sensitivity studies to see that it's functioning the way you expect.
Okay. Any golden advice, golden tips for the students to make the optimum structural design?
I would say the golden advice is you're not going to come up with your final design within the DSE. This is one of the biggest things that people lose sight of. You are constantly doing a feasibility study, is the weight targets feasible? Is the structure going to be able to be designed in order to meet the design requirements? So think about your design as assessing whether this is possible and what is the next step, rather than I just need to have something in the end, because then you lose sight of that process.
So you have to see this in the entire design, and it's not the only structure, it's not the optimum design, it has to function together with all the other elements there.
And also don't be afraid if it becomes a killer requirement. And this isn't just with structures, it's any part of the aircraft. You might do some calculations and find out that, some aspect of your design is really a problem. And it would maybe prevent progression of the design further. We have to be critical of our own designs, our own concepts, and also identify before millions of euros are spent on something that perhaps it won't be feasible in the end. That hurts a little bit, our pride, but it's very important in order to identify those moments as well.
Okay, thank you very much for the interview.
Yeah, thanks.